On slide 8, we see the outline again, and now we're ready to talk about how to search for direct effects. And I'm going to talk through a set of different approaches with a special emphasis on penalized SEM, PSEM. So there are several different approaches for searching for direct effects in LCA. So let's consider an analysis with the latent class variable regressed on all covariates. So we have C on X. And in addition to that, we have several alternatives listed here. First of all, we can regress each latent class indicator on all covariates if we have an indicator that we worry about being non-invariant. Or we can regress all latent class indicators on one covariate if we have a candidate covariate that we are worried about being a cause of a direct effect of non-invariance, like male-female. And the pro of that, the advantage is that each analysis easily converges, and the negative is that we have to do several analyses, one for each latent class indicator or covariate, depending on the alternative we choose. Another approach is to regress all latent class indicators on all covariates, and the advantage is then that we have a single analysis, and the disadvantage is that it may not converge, perhaps due to being empirically non-identified. It may not be empirically identified. We have to remember that in mixture modeling, it may be identified in principle, relying on higher order moments. If you compare with the non-identified case of mimic with continuous factor indicators, you cannot have all direct effects as well as the factor regressed on the covariates. So relying on higher order moments can be a little bit unstable, and it may not converge in all cases. Yet another alternative is the one we want to focus on here, namely, again, regressing all latent class indicators on all covariates using what we call PSEM regularization. And there are two papers related to that, the original 2024 paper and now a new follow-up paper which talks about extensions to the 2024 paper, and that includes PSEM for mixtures, that is, including then latent class analysis. And the advantage here is that it leads to parsimonious models, that is, with fewer significant direct effects, and it converges more easily for a small enough prior variance, so it can avoid the non-convergence problem that we may have up here. The disadvantage is that we have to choose prior variances, which calls for more than one analysis. So I'm going to illustrate that. So let's ask ourselves, what is PSEM then applied to finding direct effects in LCA? Again, PSEM stands for penalized structural equation modeling, and we're focusing on maximum likelihood estimation, which is what we use for mixtures, using priors. And PSEM in general uses priors for two quite different purposes. One is to estimate a model that is non-identified without the priors. So the priors add the extra information that is necessary to make the model identified. And that's very similar to what we call BSEM for Bayesian estimation, with small variance priors for parameters that would otherwise be non-identified. But it can also be used for the other purpose of simplifying models that are identified but can be fitted practically as well with fewer parameters. So that's a common situation in mainstream statistics. It's called regularized analysis, where a common prior is the so-called lasso prior, which stands for least absolute shrinkage and selection operator. And lasso is used, for instance, in regression when you have many covariates and you want to pick out those that are important and setting the slopes for the others to 0. And in our case, the example is dealing with direct effects in LCA, latent class analysis. So what we're going to do is to include all direct effects and have PSEM use either lasso or another prior that we call ALF, an in-house prior, alignment loss function, with mean and variance priors for the direct effects. And what we're going to do is to maximize a fit function, which is the sum of the usual maximum likelihood log likelihood plus a penalty. And that penalty is larger for smaller variance. So for instance, we will specify an ALF prior with mean 0 and a small variance like 0.01. Now, the 0.01 mean and variance means that we have, since it's a small variance, the penalty is larger. We have a larger negative addition to the log likelihood. And we get a larger penalty for any direct effect that deviates from the mean of 0. Now, that means that the penalty penalizes model with many direct effects. It favors a parsimonious model. We don't want to have a large penalty, which we would get if we have many direct effects. Variance equals 0 exactly would be a very large penalty and hurt the maximization of the fit function. And that would then lead to a non-PSEM analysis, a regular analysis with no direct effects, because you don't dare to have any direct effects because they'll increase the penalty. Variance infinity, or very large, is the same as a non-PSEM analysis with all direct effects. So you want to try to find something in between of the no and all. Use a variance that makes the log likelihood practically as good as with all direct effects included, but with fewer direct effects. Now here's the input. It's very simple. The theory is complex, and I'm trying to describe it in very short terms. But the Mplus run is very easy. The only thing we add are those bolded parts here in the model that we looked at before. In addition to C on X, we also have U on X. The latent class indicators regressed on all of the covariates, and there are then therefore 187 of those effects, 187 slopes in that regression, 17 times 11. And we give them labels, direct effect 1 through 187, and the model prior then is ALF for all of those parameters with mean of 0 and a relatively small variance of 0.5. And we're going to see how that works out. Here is the essence of the technique described in a picture. So on the y-axis we have the log likelihood, and it usually occupies the negative part, and the closer it is to 0, negative but close to 0, the higher the likelihood, the better the likelihood. On the x-axis we have the prior variance. So when the variance is 0 or almost 0, we have a very small variance, a very large penalty, and therefore a very parsimonious model. Here is a very parsimonious model. It's the model with no direct effects. So very small variance for PSEM is the same as a non-PSEM run with no direct effects. And on the other end of the spectrum, you have a very large variance, which is a small penalty, and a very non-parsimonious model. And here is one where you have all direct effects included in the model, of which 97 happen to be direct effects that are significant. Now you look at this likelihood that increases and then flattens out. And what you want to find is a smaller number of direct effects than 97. We started with 187 possible, 97 not significant. Now we want to reduce it down to a more manageable number, and we choose a number then somewhere on this curve where it is flattened out enough, where the likelihood value is close enough to the likelihood value here on the right. And that is obtained then with different choices of the PSEM variance values that we're going to try. And here on slide 13, you have a very intensive description of what we do, the strategy that we take. So we have the models, number of parameters, log likelihood, BIC, number of significant direct effects, and something we call log likelihood drop. So first we start out with 3 non-PSEM models. So PSEM is not involved at all. The model with no direct effects, a lot of parameters, rather few parameters, and a very large negative log likelihood, so very low and bad log likelihood. And here you have the BIC. And there are no significant direct effects because there are no direct effects. And then you have the model with all direct effects. The number of parameters jumps, the log likelihood improves, gets closer to 0 from below than the one above. But it has more parameters, and BIC gets worse. The number of significant direct effects is 97. And then let's try to do an analysis with only those 97 significant direct effects. And the number of parameters then goes down. And you have this log likelihood, which is having the best BIC of the first 3. So now we found a model that has a good BIC and 97 significant direct effects. And now we want to try to reduce the number of direct effects down without worsening this log likelihood value too much. So we have then a couple of PSEM runs for model 4, 5, 6, and 7, and 8. And we look at the log likelihood and see how much worse it is than this log likelihood. We start very low here, low negative, so bad log likelihood. And then we get up higher and higher in the log likelihood with increasing variance for the prior. And by the way, I should mention that the NA stands for not available, which means that for PSEM, as I will describe later on, the number of parameters is not a clear number. It's not clear what that number should be. And therefore, we also lose BIC here when we use PSEM. So with the lowest variance here, 0.05, we get 10 significant direct effects, but the log likelihood is pretty far from the one with 97 direct effects. Increasing the variance a little bit, get more direct effects, improving the log likelihood. And then here for 0.5, we get 42. 42 again, and then 53. So we are then moving up on this curve here by increasing the variance for PSEM, moving up and improving the log likelihood. And after we've done that, then we can get back to non-PSEM runs for the last couple of models from 9 to 13. So for instance, building on model 4 with PSEM 0.05, we had 10 significant direct effects. So we have then a non-PSEM run where we allow 10 direct effects and look at the log likelihood and BIC for that. And then we have, let's go down to model 11, which builds on model 6. So that 6 here refers to the model up here, so 0.05. For model 6, we had 42 significant direct effects. So we have 42 direct effects here. And here's the log likelihood and the BIC. And it turns out that only 41 of those were significant in the non-PSEM run. We also have the model building on the non-PSEM model 12 building on the PSEM model 7, where we also had 42, but it's not the same 42 direct effects in models 11 and 12. Both models 11 and 12 have 41 significant direct effects. Compare that to model 3, where you have 97 direct effects. So we got a big simplification here. And the worsening of the log likelihood is relatively small. If you look at this log likelihood compared to these, they correspond to only a 0.2% drop. That is worsening of the log likelihood, computed as this percentage here at the bottom. So let's take a closer look at choosing between models 11 and 12. On slide 14, why is 42 for PSEM 0.5 bolded in the graph on slide 12? Let me go back to slide 12 here. Why is this 42 bolded here? Why do I choose that over that, for instance? Well, PSEM 0.5 model 6 has a lower, that is worse log likelihood than PSEM 1.0 model 7. And both models show 42 significant direct effects, but not the same ones. Now the non-PSEM models 11 and 12, which are based on the PSEM models 6 and 7, for them, freeing the 42 direct effects results in a higher log likelihood for model 11 than for model 12, despite model 6 having a lower log likelihood than model 7. So this is why we lean towards model 11 rather than 12. We have a better log likelihood for model 11 than for model 12. Model 11 and 12 have the same number of parameters, same number of significant direct effects, and the same log likelihood 0.2% drop. Model 11, however, is chosen because it has the better log likelihood and better BIC than model 12, and it actually has the best BIC of all the models.